Imagine you ask your brand new AI assistant to log a really simple medical symptom into your health portal.
Oh, this is a classic scenario.
Right. So it goes to do it, and it realizes it doesn't actually know your password. And instead of, just pausing to ask you for it,
It just makes one up.
exactly, it just hallucinates password 123, fires it off to your healthcare provider's secure server, and just like that, it instantly locks you out of your own medical records.
Yeah, that failure mode is, well, it's honestly the biggest bottleneck in autonomous software right now. I mean, we build these massive language models, but when we let them loose in real-world systems, the translation between, knowing what to do and actually doing it, it completely falls apart.
Which is exactly why we're targeting this specific topic for you today. We know you're constantly looking for the structural reasons behind why AI behaves the way it does.
And this is a big one.
Huge. So our mission today is pulling apart a state-of-the-art paper from the foundations of the state-of-the-art Gen AI materials. It's this really fascinating breakthrough from researchers at Jilin University.
Titled Capability-Aligned Hierarchical Learning for Tool-Augmented LLMs.
Yeah, which is quite a mouthful, so we're just going to call it CAHL to save our breath. We're looking at a massive leap in how AI moves beyond just generating text in a chat window to actually manipulating tools.
Right, things like APIs, calculators, databases.
Exactly, using those to run complex multi-step tasks on your behalf.
Okay, let's unpack this.
Mm-hmm.
Why is it so incredibly hard to get an AI to successfully juggle multiple instructions without completely breaking down your software?
Well, to understand the CAHL breakthrough, we first have to understand where the current architecture stumbles, right? Which brings us to the concept of tool learning.
Okay, lay it out for us.
So large language models are fundamentally just text generators. They're trained on historical data. They do not natively know real-time information.
Right, they're trapped in the past. Like, if I want to know the current weather, the model itself has absolutely no idea if it's raining right now outside my window. Precisely. And that's exactly why they need external tools. If you ask, what's the weather in Beijing today? Just generating text fails.
Yeah.
The model has to actively decide to pause its text generation, call a weather API, input the parameter Beijing, and then use the real-time data it gets back to formulate your answer.
Got it.
We call that a simple single-turn action. One tool, one call, one answer.
Which is, fine for checking the rain, but if I'm deploying an AI agent in a corporate environment, or even just trying to manage my own personal life, tasks are almost never a single step.
They're really not. And the paper highlights a brilliant example of this complexity. The prompt is, find the average closing price of Apple stock in the past 10 days.
I mean, that sounds incredibly simple to a human. You just look up the 10 numbers and divide by 10.
Right. It sounds simple until you look at the mechanical reality of how software actually works. The AI cannot just make one magical tool call that says, do the whole thing.
Right.
It has to fetch the closing price for day 1. It stores that. Then it fetches day 2, day 3, sequentially all the way to day 10.
Wow, okay.
That is 10 separate API fetches. And only after successfully gathering and storing all that discrete data can it finally invoke an entirely different tool, like an average compute tool, to process those numbers and give you the final answer.
That's like asking a friend to bake a cake, but you're forcing them to go to the grocery store 10 separate times for each individual ingredient. Like, get the flour, then they come back. Okay, now go back for the eggs.
Yeah, that's actually a great way to picture it.
But I want to push back on this architecture a bit. I mean, if we have models that have read the entire internet and can pass the bar exam, why can't the AI just figure out the sequence of these tools on its own in one giant step? Why does it get stuck?
Well, because asking a standard single-turn AI to do this creates a massive bottleneck in its working memory and logic sequencing. A single tool invocation simply cannot cover the multiple steps required.
So it just overloads.
Exactly. The AI tries to shove a 10-step logic puzzle into a one-step action box. It might try to call the closing price tool once and just feed it the number 10. But if that specific API tool is only hard-coded by the developer to retrieve one day at a time,
the server just rejects the request.
yes, the whole process crashes.
Yeah.
A standard model fundamentally lacks the architecture to sequence out a long chain of events natively, wait for the results, and then pivot based on those results.
Okay, so that means developers had to build a workaround if they wanted these models to be useful in the real world. I'm guessing this is where they introduced some sort of management structure to force the AI to break things down.
You nailed it. That's the exact evolution of the technology. Developers introduced what is known as a plan-then-execute hierarchy.
Plan, then execute.
Right. If a single neural network can't juggle the entire workflow, You split the AI into two distinct specialized roles. You have a high-level planner and a low-level executor.
Oh, I see. We're bringing in corporate management, we've got the big picture executive, and the detail-oriented specialist.
Exactly. So the high-level planner receives your query about the Apple stock. It analyzes the goal and generates a list of subtasks. It says, Subtask 1, fetch the 10 days of prices individually. Subtask 2, calculate the average.
Makes sense.
Then it hands those instructions down to the low-level executor, whose entire job is to translate those subtasks into concrete, perfectly formatted code to actually trigger the tools.
Having a visionary planner and a heads-down coder makes logical sense. It solves that context bottleneck you mentioned earlier. But clearly, based on the Jilin University research we're looking at, something in this setup is deeply broken.
What's fascinating here is the fatal flaw in how we actually build these two systems. Currently, in standard hierarchical models, the planner and the executor are trained and optimized entirely separately from each other.
Wait, separately?
Yes, they do not share a brain.
Oh, that's wild. That's like an architect drawing up this visionary, beautiful blueprint for a skyscraper. That's our planner. But it's physically impossible for the construction crew, the executor, to actually build it with the specific hammers and cranes that they have in their trucks.
That's spot on.
It's like the architect never even bothered to look inside the crew's toolbox.
That is the perfect analogy for what the paper calls planner-executor misalignment. Let's dive deep into the mechanical breakdown of that. The planner might create a subtask that is way too coarse. It tells the executor, average Apple's closing price over the past 10 days.
And the executor.
The executor looks at its available software tools and essentially says, I don't have a magic 10-day average button. I only have a tool that fetches a single day's price. The subtask exceeds the executor's capability, so it just errors out.
Right, the manager just yelled, fix it, without telling the specialist how, and the specialist doesn't have a fix-it button.
Exactly. And it can also fail in the opposite direction. The planner might become incredibly fine-grained, trying to micromanage the executor.
Oh, nobody likes a micromanager.
Right. It might generate this massive chain of rigid logic. Get day 1, get day 2, get day 3, when maybe the executor actually does have a new specialized tool for pulling the past end days' closing prices in a single batch.
So it's just wasting time.
By forcing unnecessary low-level details, the planner creates messy, inefficient code that wastes a ton of compute power.
And since the executor is trained separately, I assume it also completely misinterprets the planner's underlying goal sometimes. Like, it might receive the instruction, get Apple's closing price of past 10 days, then average prices, and somehow decide to call the average compute tool first before it even has the prices.
Constantly. Just blindly matches the word average to the average tool without understanding the sequential intent. It gets the order of operations totally backwards.
Okay, to truly grasp the stakes of this misalignment, we need to move away from abstract stock prices. I mean, a broken stock fetch is annoying, sure, but I want to look at a scenario from the paper where this architectural flaw becomes actively dangerous.
Yes, the Jerry case study.
Exactly. This moves us into the realm of sensitive personal data.
The medical profile scenario perfectly illustrates the structural terror of misalignment.
Okay, so the prompt in the paper is this. A user says to the AI, I have been experiencing migraines. Please update my medical profile to register this new symptom. My username is Jerry, and the required password is ZXCVBN.
It is a highly constrained task. It requires the AI to recognize personal identifiable information, maintain an exact sequence, and perfectly retain data constraints.
Right. So walk me through how the standard decoupled AI baseline, where the manager and specialists are trained separately, how does it handle poor Jerry's request?
Well, the decoupled planner analyzes the user prompt and generates an overly abstract instruction. Because it isn't trained on the rigorous mechanics of APIs, it just outputs, update the user's medical profile with the new symptom.
Wait, it just completely strips the password constraint out of the blueprint?
Entirely. The planner thinks the password is just, like, peripheral context, not a strict structural requirement for the tool to function. It passes down the username Jerry and the symptom migraine, but nothing else.
Oh boy. Here's where we need to clarify what happens next, because it's crucial. The executor receives this vague instruction, but the executor has to interact with an API schema.
Yes.
When we say API schema, we basically mean a rigid, unchangeable, fill-in-the-blank form that the healthcare software requires, right? Like, if the form has a mandatory blank space for a password, the executor can't just skip it Or the server rejects the whole thing.
That's an excellent way to describe an API schema. It is a ruthless digital bouncer.
A ruthless digital bouncer. I like
It
that.
requires exact inputs. So left entirely without the password from the planner, the executor is staring at a mandatory field. It's programmed to complete the form to make the tool run. So what does it do? It hallucinates.
It just makes one up.
Yes. In the paper's example, it simply invents a string and inserts password 123 into the secure password field.
That is a total disaster. It's firing a fake password at a secure medical server.
Which results in a fatal API authentication error. The tool rejects the payload, the profile isn't updated, and the task fails entirely.
Think about what this means for you. If you are trusting an AI agent to handle your personal software, your banking transfers, your health records, a misaligned AI doesn't just quietly fail to do the job.
No, it doesn't.
It actively fabricates data to try and force a square peg into a round hole just to complete the subtask. Hallucinating a password is a massive liability. It could trigger security protocols and lock you out of your own accounts.
Which is exactly why it moves this problem from an academic puzzle to a fundamental safety requirement. We cannot deploy autonomous agents at scale until the planner and executor are structurally aligned.
Which brings us to the actual breakthrough from Jilin University, CAHL, Capability-Aligned Hierarchical Learning. We've seen the disastrous results of keeping the manager and the worker in separate silos. CAHL's solution is forcing them to work together. How mechanically does it achieve that?
CAHL completely abandons separate training. Instead, it jointly optimizes both the planner and the executor simultaneously using a technique called reinforcement learning with verifiable rewards, or RLVR for short.
Okay, reinforcement learning is a term we hear a lot, but let's break down the how here. We aren't just feeding it data to read. We're setting up a massive trial and error environment where the system tries a task, gets graded, and mathematically adjusts its own internal weights based on that grade over thousands of iterations.
That is exactly the mechanism. And the verifiable rewards part acts as the ultimate grading rubric for those iterations. Because it's a hierarchy, CAHL applies two distinct but interconnected grading systems at the very same time.
Okay, let's hear them.
Let's look at the high-level reward for the planner. It is judged mathematically on two criteria. First, parameter-level rewards.
Let me guess. Parameter level basically means reading comprehension. Did the planner actually extract the correct real-world parameters from the user's prompt? Did it grab the string Jerry, the string migraine, and the exact password?
Spot on. If it drops the password, it receives a negative reward signal, and the model adjusts its weights to pay closer attention to constraints the next time around.
Makes sense.
But the second criteria is the true innovation. Execution-level rewards. The planner's score is explicitly tied to whether the plan actually worked for the executor down the line.
Wait, so the planner gets penalized if the executor messes up the final task?
Exactly.
I love this. Let's stick with the corporate analogy. CAHL just tied the executive manager's end-of-year bonus directly to the specialist's performance review.
That's exactly what it does.
Suddenly, that manager is deeply incentivized to make absolutely sure their instructions are perfectly clear, achievable, and meticulously tailored to the specific tools the specialist actually knows how to use. They can't just hand down a vague mandate and blame the worker when it fails.
The manager is forced to learn the worker's language. It's brilliant. But we also have to grade the worker. That's the low-level reward for the executor, which is graded on three rigorous criteria.
Okay, what are they?
First, format. Did it use the correct XML tags to structure the data? Like if the system expects open bracket, password, close bracket, did it actually use those specific tags?
So it's grading the underlying structural grammar.
Second, syntax. Did it strictly follow the API schema constraints? For example, if the tool requires a numerical integer for a date, but the executor passed it a string of text spelling out the word Tuesday, the syntax fails, and it receives a negative reward.
It's punishing the AI for trying to shove letters into a numbers box.
Precisely. And third, semantics. Assuming the format and syntax are perfect, did it actually use the right tool, call the right parameters, and input the exact correct values to solve the original intent?
Okay, so under this CAHL system, with thousands of trial and error runs teaching these two layers to synchronize, let's run the Jerry migraine scenario again. How does the jointly optimized system handle it?
Well, because the planner has been mathematically trained to care about the executor's success, its behavior fundamentally changes. It no longer drops the password because it knows the executor's API schema will demand it.
Right, learn the hard way.
Exactly. The CAHL planner explicitly anchors all constraints in its subtask. It outputs call personal info update tool. Username is Jerry. Symptom is migraine. Required authentication. Password must be ZXCVBN.
It provides the high-level visionary blueprint, but also hands over the exact raw materials needed to actually build it.
The executor receives this capability-aligned instruction. And because it now has everything it needs to satisfy the API schema, it faithfully fills out the secure form. Format is correct, syntax is correct, semantics are correct.
No hallucinations required.
None. The task succeeds, the medical profile is updated, and both the planner and executor receive a positive reward signal.
The architecture works in harmony. Now, the theory is incredibly elegant, but anyone can write a paper showing their model succeeding in one hand-picked case study. When you take this CAHL architecture and throw it into the messy reality of actual software environments, does it actually prevent AI from hallucinating and failing?
The researchers ran extensive evaluations, and the numbers are remarkably robust. They benchmark CAHL against some of the most capable tool learning baselines in the industry right now.
Yeah, looking at the data here, they tested it against heavyweight open source models like Qwen, Tool-N1, Tool-RL, ToolSample, and EasyTool. And they didn't just use one test, they ran it across open-ended environments like Bamboogle and incredibly strict multi-step environments like BFCL and API Bank. It looks like a clean sweep for CAHL.
It really is. The API Bank metrics are the most revealing because API Bank is explicitly designed to test complex, multi-turn interactions. Let's look at the reduction in failure modes.
Okay, hit me with the numbers.
First, we measure the redundant call ratio. This tracks how often the AI gets confused and just spins its wheels, calling the same tools over and over without making any actual progress. The baseline Tool-RL model had a redundant call ratio of nearly 12%. CAHL dropped that down to a staggering 1.51%.
Wow. That tells me the system is incredibly decisive. Because the blueprint is aligned with the tools, it doesn't second-guess itself or get trapped in those endless logic loops.
Exactly. Next is the critical safety metric. Invalid tool calls. These are the fatal errors we discussed earlier: hallucinating a password, failing the syntax, or calling a tool that just doesn't exist.
The scary stuff.
Right. Tool-RL failed with invalid calls over 30% of the time. Think about that failure rate in a commercial setting.
Unusable. I mean, you can't have your software crashing 1 out of every 3 times you ask it to do something.
CAHL nearly cut that error rate in half, dropping invalid calls down to 16.92%.
Still not perfect, sure, but a massive jump in structural reliability for real-world application.
And finally, sheer efficiency.
Yeah.
CAHL completed the successful tasks using fewer average steps, 1.04 steps on average compared to 1.24 for the strongest baseline. It arrives at the correct execution faster, utilizing fewer unnecessary actions.
Okay, so the CAHL architecture creates an agent that is decisively smarter, significantly safer from hallucinations, and spins its wheels way less. But whenever we look at a state-of-the-art breakthrough, we have to look for the catch.
There's always a catch.
Right. There is no way running 2 grading systems simultaneously through reinforcement learning comes for free. I have to imagine this absolutely chews through computational power.
If we connect this to the bigger picture of AI development, hardware constraints are always the invisible toll booth. Running a jointly optimized hierarchy requires substantial computational overhead. The researchers note that the memory usage during training jumps from 15 gigabytes for a standard baseline model up to 36 gigabytes for CAHL.
Oh, wow. It's more than doubling the required memory footprint just to get the manager and the worker on the same page.
It is, and that overhead impacts the end-user experience too. The inference time, which is the actual clock time it takes the AI to process your multi-turn task, communicate between the planner and executor, and trigger the tools increases significantly.
How much are we talking?
In their multi-turn tests, inference time jumped from 7.79 seconds on baseline model to 13.21 seconds for CAHL.
You know, here's where it gets really interesting, though. A 5-second delay in inference time sounds bad on paper, but as an actual human user trying to automate my life, waiting an extra 5 seconds feels like absolutely nothing.
Very true.
If waiting 5 extra seconds is the compute tax I have to pay to guarantee the AI actually executes a 10-step software workflow correctly, instead of locking me out of my healthcare portal with a hallucinated password, I am paying that tax every single time.
Without hesitation. From a product perspective, it is a highly favorable trade-off for the sheer execution reliability you gain in return.
It changes the entire paradigm of trust. So let's take a step back and recap this journey we've taken today. We started by looking at the hard limits of single-turn AI, why simply generating text fails when you need to fetch 10 days of Apple stock and compute an average.
Right, the one-step box.
Exactly. Then we explored the initial fix-splitting the AI into a high-level planner and a low-level executor, but saw how training them in isolation led to disastrous miscommunications, causing our AI to literally invent passwords just to fill out forms.
The Jerry scenario.
Poor Jerry. And finally, we unpacked the capability-aligned breakthrough, using reinforcement learning with verifiable rewards to force the manager and the worker to train together, ensuring the visionary blueprint perfectly matches the tools in the toolbox.
It emphasizes a core belief we return to often on this show. Critical thinking about system architecture is essential. Knowledge isn't just about knowing what a model outputs, it's about understanding the internal mechanisms.
Yeah, peeking behind the curtain.
Realizing that there is a planner and an executor talking to each other inside the black box helps you, the listener, diagnose why your own AI tools sometimes succeed brilliantly and other times fail inexplicably. It strips away the magic and reveals the mechanics of how software learns.
Which is the exact reason we dig into these state-of-the-art papers. And I want to leave you with a final thought to mull over as you go back to your own projects today. As AI models rapidly adopt these capability-aligned joint reward structures, they're transforming from glorified chatbots into highly reliable, autonomous digital delegates.
They really are.
So think about your own daily workflows. If an AI could reliably execute a complex 10-step digital chore for you, taking just a few seconds longer to guarantee it doesn't hallucinate a single variable or break any APIs, what is the very first mundane, multi-step task you would hand over to it tomorrow morning? Think about it. Because that level of true delegation is arriving a lot faster than you think.
Until next time.